Imagine waking up and the ground beneath your feet just stops. For 5 seconds, the Earth's rotation halts completely, but the atmosphere and the oceans, they keep going. To understand the mechanics of this disaster, think about riding in a car. If you're traveling at 100 kilometers per hour and the driver slams on the brakes, your body doesn't stop. It keeps moving forward at 100 kilometers per hour until something stops you. That's the law of inertia. Scale that up to a planetary level. Our planet is the car, and everything resting on its crust, buildings, forests, and you, are the passengers. Astrophysicists like Neil deGrasse Tyson have pointed out the gruesome reality of this physics problem. The bedrock freezes, but anything that is not physically anchored to it is instantly launched sideways at supersonic speeds. The lethality comes from the unyielding momentum of the world itself. While the bedrock anchors in place, the atmosphere and everything within it maintain a speed the ground can no longer match. This 3D wireframe shows us that the Earth's rotational speed is entirely dependent on your latitude. It's fastest at the equator, moving at roughly 1,670 kilometers per hour, and it steadily drops as you move north or south, reaching virtually zero at the poles. Space agencies actually rely on this high-speed zone. When NASA launches a rocket, they prefer to do it as close to the equator as possible. By launching in the same direction the Earth is already spinning, the rocket gets a massive free velocity boost to help it escape gravity. Reaching orbital destinations like the International Space Station requires highly precise calculations to match that existing rotational momentum. The Earth is basically doing a large chunk of the heavy lifting. But that rotation also creates an outward push, centrifugal force, which actively counteracts gravity. If the spin suddenly drops to zero, that outward push disappears. Anyone standing at the equator would suddenly weigh slightly more. The exact region that gives our rockets the momentum they need to reach the stars would instantly become the most violent place on the planet during a sudden halt. The ground might be frozen, but the atmosphere is an independent fluid mass. It retains its momentum, meaning the air itself is still moving eastward at over 1,600 kilometers per hour. This creates supersonic winds. We're talking about gusts traveling significantly faster than the speed of sound, dwarfing any recorded hurricane. These winds would scour the surface, flattening man-made structures and ripping topsoil right off the bedrock. Earth's constant spin pulls the oceans toward the equator, creating an equatorial bulge held by the outward force of rotation. When the spin stops, that force vanishes. Gravity takes over, and that massive volume of water immediately rushes toward the poles. The geography of the planet would be instantly rewritten. Massive tracts of land would emerge around the drained equator, while the northern and southern hemispheres would be swallowed by catastrophic high-velocity megatsunamis. The shape of our coastlines, the placement of our oceans, and the safety of our air all rely entirely on the planet's constant, unceasing motion. Then the 5 seconds are up. The Earth's bedrock instantly jolts back into its normal rotation, violently slamming right into the already chaotic, high-speed atmospheric currents and surging oceans. This is the whiplash effect. The crust is suddenly accelerating, but the internal layers, like the dense core, are still fighting for momentum. The resulting friction would trigger global earthquakes and force massive volcanic eruptions to breach the surface. Fortunately, this scenario is a physical impossibility. Our planet's spin is a product of the conservation of angular momentum, a leftover force from the swirling dust and gas that formed the solar system billions of years ago. There is no natural force capable of applying enough friction to stop it. Inside the Earth, this continuous rotation drives the liquid iron outer core. According to dynamo theory, the swirling, convecting metal acts as a massive generator, sustaining the planet's protective magnetic field. The mechanics of this internal generator are incredibly complex. In fact, Albert Einstein once considered the exact origin of the Earth's magnetic field to be one of the greatest unsolved problems in modern physics. So while atomic clocks show that the Earth's rotation does fluctuate by fractions of a millisecond over the years, the immense energy of the geodynamo ensures the planet will keep spinning for billions of years to come. The constant, dizzying speed of our planet's rotation is the physical boundary keeping a stable, living world from becoming a wasteland of supersonic storms.